Good morning. I'd like to welcome you to the EMC Live webinar, Troubleshooting Today's EMI Problems. My name is Helen Flood, and I will be administering this webinar today. I'm the project manager at Interference Technology, the host and creator of this event. EMC Live is a new and innovative 3-day online event hosted by Interference Technology. This event highlights practical information and topics and will include roundtables, webinars, and videos on everything EMC related. Best of all, there is no cost to attend. Please visit the event website at www.emclive2014.com and plan on joining us for the other sessions over the course of the next 3 days. This webinar is presented by Ken Wyatt. Ken is Senior EMC Engineer at Wyatt Technical Services. He holds degrees in biology and electronic engineering and has worked as a product development engineer for 10 years at various aerospace firms on projects ranging from DC-DC power converters to RF and microwave systems for shipboard and space systems. For over 20 years, Ken has worked as an EMC engineer and has been an independent EMC consultant since 2008. This webinar is sponsored by our platinum sponsor, Rohde & Schwarz, one of the world's largest manufacturers of electronic test and measurement, communications, and broadcasting equipment. EMC and EMI test equipment and systems from Rohde & Schwarz determine the causes and effects of electromagnetic interference. For more information on Rohde & Schwarz, visit www.emc.rohde-schwarz.com. A recording of this webinar and download of PDFs will be available on our website. Our webinar today will be interactive. We encourage you to ask questions at any time during the session. Take a look at your GoToWebinar navigation pane, the box you see in the corner of your screen. If at any time you have a question, we ask you to use the type box and hit send. To minimize or maximize the screen, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. This presentation will last for 35 minutes, followed by a 10-minute question and answer session. At this time, I would like to hand the webinar over to Ken, who will begin the presentation.
Well, thank you, Helen. And greetings to all of you who are on the air here with me today. We're going to be talking about troubleshooting today's EMI problems, and some of the EMI problems that I experience may not be the same ones you do, but these will be the top 3 that I consider. But before we talk about that, I just wanted to give a short definition of EMC, just so everybody's on the same page here. Electromagnetic compatibility means that products don't interfere with their environments, and that would include emissions, and that the environments don't upset the operation of your product, and that would encompass immunity. There's a third aspect, though, which is becoming more and more important, and that's to do with signal integrity, where the product doesn't interfere with itself or distort internal digital signals. And EMC is really the whole concept is compatibility. We'll be talking about EMI, which is electromagnetic interference, and RFI is also associated with that, radio frequency interference. So let's move on. So the issues that I seem to deal with quite often in my own consulting are these 3. It's radiated emissions, radiated immunity, and electrostatic discharge. Now, why is this? I feel that probably the number 1 issue is product designers continue to violate EMC good design practices. And we'll be talking about that in slides coming up. But I think also the issue is digital circuits are being powered by lower and lower supply voltages. We started out with 5-volt logic, and then 3.3 and 1.8, and now even 1.2 or lower. And as the supply voltage drops like that, the noise margin also drops. And so it doesn't take much of an energy source to disrupt digital circuitry. In addition, there's a lot more low-cost mobile devices that may or may not be designed well, as well as a proliferation of wireless and high-power transmitters. The radio spectrum today is just becoming more and more crowded with wireless devices, which can impact each other. So here's some common design issues which lead to radiated emissions, and these are all things that I have noticed in my clients' products, and in no particular order actually, but things like discontinuous current return paths, which really is an issue on the circuit board. Poorly terminated I/O cable shields, that happens so often that you know, it's something that's easily solved, but I run into it all the time. Poorly designed shielded enclosures leading to slot radiation, and then LCD displays. I'm going to be talking a little bit about LCD displays because for whatever reason the manufacturers of these display panels don't make it easy to bond the panel to the shielded enclosure of a product. All these factors can cause radiated emissions, as well as susceptibility to radiated sources and ESD. We're going to be talking about all three of these issues and how to troubleshoot them. I like to refer to, when I'm doing my own troubleshooting, to a source path receptor model that I just keep in mind. And there's a model for emissions and a model for immunity. And just taking the emissions as an example, we have some kind of energy source and a coupling path for that energy, either through conducted, radiated, inductive, or capacitive coupling. And then that gets coupled to some kind of antenna structure, and that typically causes your radiated emissions. Immunity, on the other hand, we have some kind of external energy source like ESD or a two-way radio broadcast nearby, and they also get coupled through the same phenomena, either conducted, radiated, inductive, or capacitive coupling. And that can either disrupt your digital circuitry or sensitive analog circuits. I'd also like to touch briefly on common mode currents and how they're generated. Now, common mode currents are also referred to as antenna currents in some circles, but your differential current, which is the digital circuit, would be represented by the blue arrows, where you have a path from circuit 1 to circuit 2 and returning the return current coming back from circuit 2 to circuit 1. That's your differential mode current, or your signal current. But how does the common mode currents occur? And I think most of us know that it's the common mode currents that are usually the issue for radiated emissions. But if you take a look at any ground return structure or ground plane, you'll realize that there is going to be a certain impedance across any 2 points, and anytime you have an impedance, it will create small voltage sources, and these voltage sources are what push the common mode currents. There's several ways of creating common mode currents. This is one of them. But anytime you have unbalanced geometries, that can cause common mode currents in your transmission lines, for example. There's a couple equations that are pertinent. I'm not going to get too deep in the math here today, but it's possible to calculate the E field signal using from a differential mode current. Differential mode currents flow in loops, and so this equation represents the or calculates the E field given the differential current ID, the frequency F, the length of the loop L, and S is the spacing between the loop and its return path. So LS is actually the loop area. And then D is generally the measurement distance between the product and antenna and measurement antenna. D would be typically 3 meters or 10 meters. And so given a loop and a frequency and a current, you can calculate the E field from that. Typically, because we mount or we design our circuits using ground planes or signal or power return planes is a better way to describe that. These loop areas are very small, and so you can see that there's a constant 2.63 times 10 to the minus 14. That's a very small number, and so typically the E fields from current loops are small and insignificant. On the other hand, common mode currents, you can see that the constant is orders of magnitude bigger number. It's 10 to the minus 6. It's a similar equation, but high frequency common mode currents are currents that typically flow in wires or other resonant structures. And so you can measure the common mode current using a current probe, which I'll show you in a little while. And so you can measure IC, the common mode current. You know F, which might be the harmonic that is failing the limit. L is the length of the wire, and D again is 3 meters or 10 meters. And so you can, by measuring the common mode current in that wire at a particular frequency, you can predict whether you will pass or fail the limit for radiated emissions. So it's a very useful equation, and if you take a look at my blogs that I do for EDN.com, you'll see some postings on how to use that equation. So here's some examples that I've run into recently. Here's an example where the cable shield was not connected, and you know, a lot of designers just are confused about what to do with cable shields. And typically you want to bond them at each end. And so in this particular case, the cable was not, the cable shield is not connected at either end. And so this shows how we were able to do a little troubleshooting and be able to bond that to the structure. Here's another case where cables were penetrating right through a shielded enclosure, and without bonding the shields to the enclosure. And this can create, well, it can allow the cables to either receive energy, which was the case in this particular product. RF energy was being picked up by the cables and disrupting the digital circuitry. This is an issue that we watch for. Now, for LCD panels, as I mentioned previously, manufacturers don't make it real easy to bond these to your shielded enclosure, and therefore, given the physical dimensions of these, they can typically radiate around 500 or 600 megahertz, and it turns out the video LVDS signal has fairly sharp edges on it, and the digital video is clocked at a very high frequency. In one particular case, over 400 megahertz, and so that can cause the panel to resonate and then emit. Discontinuous return paths is another issue that happens often enough that I actually have a demonstration during my seminars, which is pretty eye-opening. But here in this example, there's two issues. We're running a digital signal across an analog plane, which can contaminate that plane and contaminate any sensitive analog signals on that. But if you look at the return path, that signal is crossing a couple of gaps, which, as you're probably aware, the return path tries to follow directly underneath the signal path, but in this case it's being forced out around, and so that's a very strong source of common mode currents. And of course, any I/O connector, I/O cables attached to this circuit board are going to start resonating at various frequencies depending on the length of the cable. And I'll show you an example of that coming up. So here's what happens. If we have a source feeding a load, in this example with a gap, you can see that the return current in green is being forced out around. But if you consider the H field around each of those wires, the fact that the return path is now spread out away from the signal path, it forces the H fields to actually wrap around the entire circuit board. People don't realize that, but in wrapping around the circuit board, these H fields now couple in energy from that one trace to all the other neighbor traces, and so in doing so, you've imposed signal integrity issues as well as producing common mode currents. Here's an actual example of board that I worked on a few years ago. Circled is a gap that is right underneath a digital memory chip, and by bridging that gap with a piece of copper tape, we were able to reduce the emissions by 17 dB, just that one change on the board. But what was happening was the return currents were being forced around that gap and coupling into that I/O connector just to the left of the circle. And so anything plugged into that connector would radiate. Now this is a demo that I give during my seminars. I'm going to attempt to do it here through the webinar. But in this example, we have two BNC connectors with two circuit traces. Each circuit trace is terminated in approximately 50 ohms, and one trace is over a gap and the other trace is over a solid plane. This is an idea that or an example that I got from Doug Smith some time ago, but it's a perfect example of why you don't want to run a trace over a gap. So here's the best I can do during a webinar, but on the left, we're driving the trace over a gap and measuring the signal with a near-field loop probe. Now the signal that I'm connecting to that trace is simply a comb generator, which is essentially just a pulse generator with very sharp edges. And so I'm moving the probe along, and you can see there's two traces in the scope. The top trace is the voltage that's being measured by the probe, and then the bottom trace is the spectral content. And you can see that as I'm running that probe along, the spectral content is about the same, but as soon as I get to the gap on the right-hand picture, you can see that the spectrum has increased about 10 dB or so, and you can see the voltage has just about doubled. Now there's another interesting experiment you can do with this board, and by the way, these are easy to make and use to demonstrate the concepts to your colleagues. What we've done here, in the left picture, I have attached a 1 meter long clip lead to the plane of the board. It doesn't matter where you connect it. It can be connected anywhere on that return plane. And I'm driving it with the comb generator. On the left, I'm driving the trace that is over the plane, the solid plane. And I'm measuring the common mode currents in that clip lead. And you can see that the current probe is right here with the yellow cable. And here's the clip lead. And we're driving this trace right down here, this bottom trace over the solid plane. You can see that there's a little bit of harmonic content here, but not much. And we're hardly measuring any voltage. Now, in the right-hand picture, we're driving the trace over the slot, and you can see right here we're measuring some harmonics that are resonant around 150 megahertz here and 300 megahertz here. This is the properties of the cable. This is the cable resonance occurring, but these harmonics have jumped up 10 to 20 dB, and so this is the issue, running traces over gaps. So what do you do about troubleshooting radiated emissions? We use near-field probes, and we identify possible sources using those, but not all structures that we measure are really going to radiate. It depends on the wavelength of the structure. And I blogged on this. There's a reference at the bottom of the page here that you might want to go to. Now the other thing we use is current probes. Here's an example from Rohde and Schwartz that will measure frequencies from 1 to 250 megahertz. And again, by knowing what the common mode current is in that cable, you can predict whether your product will pass or fail. That's a very powerful technique. Here's an example that I blogged on recently where we're demonstrating cable resonance. And very often the product will fail in frequency bands such as this peak here. Might be a failure point, and it depends on the resonant structure of the cables, or the resonant length of the cables. Here's a close-up picture of that resonance, which occurs at about 88 megahertz for this 1.3 meter cable. And I might point out that this we're actually using an oscilloscope here from Rohde & Schwarz. The top trace here is the voltage, and the bottom is the FFT of that voltage. Setting up for radiated emissions troubleshooting. Generally what I do is I'll take the product under test that we're going to troubleshoot, set it up on one end of a workbench, and then I'll set up an antenna and spectrum analyzer on the other end of the workbench about a meter away. And that way, as I'm troubleshooting, I can see in real time whether I'm making improvements or not. Here's a case where we've actually set up a 3-meter measurement site in an office, and this is easily done, and we can use this kind of a setup to give us a rough estimate of whether the product is failing or passing. This is a typical pre-compliance receiver or EMI receiver. This particular one is from Rohde & Schwarz, which works quite nicely for doing pre-compliance testing. Now, I'd like to move on to radiated immunity and then later ESD. And for radiated immunity, one of the things I like to use for troubleshooting is simply a two-way radio. In this case, the example is an FRS radio, family radio service, and this transmits about 465 megahertz. But it's actually a pretty useful tool for checking your circuits. And there's various license-free radios from Citizens Band to the FRS to other things like mobile telephones. And I've actually measured several, and you can see that the FRS radio, for example, is about 2 volts per meter at a 1 meter distance. So this is a handy chart you can use to estimate field strengths. One of my favorite techniques, though, is using a signal generator and a near-field probe. That way you can control the frequency and amplitude and be able to zero right in on some susceptible part of your circuit. In the right-hand photo, we show a very small ribbon cable that was susceptible to about 900 megahertz, and by probing that one cable, we could see the display on this medical product was being disrupted. But putting the probe anywhere else on the circuit board or on any of the other ribbon cables had no effect. So it was very easy to narrow down the problem. I did some recent blogging on measuring the actual field level from several different models of near field probes, and you can see that some of the E fields 2 millimeters away were fairly high, 6 to 8 volts per meter. Here's some measured E field probes, and they were, some of them were around 3 to 4 volts per meter, and the other was even higher. But you can use these near field probes to create a small focused field for troubleshooting. You might wonder whether these feeding an RF signal to a near field probe would cause interference, and the answer is probably not. This is a chart of E field versus distance for several different probes, and you can see that after about 1 or 2 centimeters distance, the field level was essentially 0. Another interesting way of creating a radiated immunity check is by constructing a chattering relay, and these are kind of cool. But they produce a very broadband RF signal, which can check many frequencies simultaneously. So it's a very quick check on your circuit by holding this near. And all you do, of course, is wire the normally closed relay contact through the coil. When you plug that into the AC or DC supply, you'll discover why it's called a chattering relay. Moving on to ESD, this is another very common failure mode that I run into all the time. On the left, you'll see the ideal or idealized ESD waveform. Now, ESD can approach 30 amps of current on the peak there. On the right-hand side is an actual measured ESD pulse using a 6 gigahertz bandwidth oscilloscope. So for ESD, I mean, that's a fairly high energy source, and there's a number of ways of controlling that. The best way is to divert it around your circuit using a shielded enclosure. Not all products can afford a shielded enclosure, so that's where it gets a little tricky. Basically, what you know during the ESD test, we test to the I/O connectors and various parts of the product that can be touched by a human, and so the idea is we want to either divert or block the ESD and this is one idea here as to how to divert the current around your circuitry, is by providing a lower impedance path around the board. But typically you'll want to, especially for products that don't have shielded enclosures, you'll need to put transient protection on and common mode filtering. Here's a case where a microprocessor board was being reset by ESD just by people walking by on the carpet, and trying to plug in the I/O connectors would reset the CPU. What was happening here, the CPU reset line was being run all over the board, and so any kind of charges anywhere introduced on that board or near the board would cause the CPU to reset. So by putting an RC filter on the reset pin of the microprocessor, we were able to filter out those ESD impulses and fix the issue. But you know, it's surprising, a lot of inexpensive microprocessor boards don't have proper filtering. Here's another idea from my colleague Doug Smith. Simply putting a few coins in a sandwich bag and jiggling them will cause considerable ESD, and so jingling these coins near your product is a good test during troubleshooting. You can see we're measuring as little as 30 picosecond edges just from the coins, and the oscilloscope display there is 500 millivolts or a half a volt per division, so we're getting several volts peak to peak from these coins. So let me just summarize. Most EMC problems I've found can be traced to poor PC board designs which cause common mode currents. It's also traced to faster than necessary edge rates, poorly bonded cable shields, and poorly routed cables leading to coupling to resonant structures, and as well as poorly designed product enclosures. And what I find is the best tool is a spectrum analyzer or EMI receiver, such as Rohde & Schwarz's ESR-P. These are really the instruments of choice when doing troubleshooting, because it allows you to see at a glance the overall harmonic emissions spectrum. These instruments are also really handy for pre-compliance testing, and I have set up 3-meter measurement sites in conference rooms, in basements, and office cubicles. And yes, you have to deal with ambient signals from radio and TV and so forth, but if you know the major harmonic emissions, you can zero in on just those and ignore the ambience usually. Now, an oscilloscope is also very useful for measuring edge rates, ringing on waveforms, and noise voltages in ground planes and power buses. And I've had a chance to use Rohde's RTE 1104, which is what was pictured in some of these slides. What's unique about this particular scope is that it has a 1 millivolt per division sensitivity, and not all digitizing scopes are this sensitive. And because it's so sensitive, it's very useful when you switch in the FFT spectral analysis. Now, if you look at my website and some of the other blogs and articles that I've done, you'll see much more in the way of troubleshooting probes and equipment and that kind of thing. So having the right probes and equipment is useful for troubleshooting these 3 particular issues. And you always want to consider the path of current. Digital designers don't always understand that it's the current that's important, not the voltage. And typically the return currents are usually undefined when you design your circuit board, and if the return currents have an undefined path, you're just asking for trouble. So that's the end of the talk. There are some references here if you'd like more information. Rohde & Schwarz has a good website section in there on their web on EMC and various test solutions. They also provide an EMC pocket guide, which is a quick reference that it includes a lot of handy formulas and so forth, and design techniques. And that was authored by myself and Randy Jost. Patrick, Andre, and I recently published our EMI troubleshooting cookbook, which is pictured there in the middle, and that's available from Amazon. And I'd also encourage you to check out my my blog on EDN and other articles in interference technology. So with that, I think we'll wrap up. And if you have any questions, I'll entertain them right now.
Ken, thank you so much.
Now, Helen, I'm not showing
We will give another, I'd like to take this opportunity to call for final questions. As Ken said, he'd be happy to answer field questions from the audience for a few minutes before we complete our session.
Now, I'm not seeing any questions on my panel here, so are you seeing any questions?
We've had a few questions.
We've had a few questions, Ken.
Okay, why don't you run through some of those and I'll try and answer them, because I'm not seeing them here in my...
Okay. One of our attendees has asked, which is the best way to reduce emissions from LVDS flat flexible cables?
Okay, good question. So LVDS, it's a low voltage, but uses pretty fast edges. And the trick is to on the cable, the trick is to keep those signals balanced, and that's not always easy. I've found a couple techniques that help as far as reducing emissions due to that cable. One is to put a ferrite over the cable, ferrite choke. The other is to run a return plane along one side. If it's a flex cable, putting a return path helps usually. And of course that return path needs to be connected to digital return at each end, and that's not always the easiest thing to do, but that's what's needed. Now I can answer that in more detail in my what I plan to do is on all your questions, I'll be answering them on future blogs on edn.com. So if we don't get to your question, be patient, and I'll try and get to them in writing.
Yeah, that would be great, Ken, because we have received many thought-provoking questions that I think you will have to address on your blog, but I think there might be time for one more. And
okay.
this attendee asked, during the jiggling bag experiment for ESD, do you need to touch the bag to the DUT to create the ESD?
Oh, good question. Just the fact that the coins are bumping into each other within on the inside of that bag will create the ESD. So no, you don't need to touch the bag to your product at all. In fact, just holding it a few inches away is more than enough coupling to the product. So yeah, that's a great question.
Thank you so much. Unfortunately, we don't have time for any more questions. We don't have time for any more today, but as Ken mentioned, he will address each of the questions you provided, and we will get the information on our site and in his blog. So you can refer back to www.emclive2014.com. Also, feel free to email us at info@emclive2014.com with any specific inquiries, and we'll direct you accordingly. Please be reminded that a recording of this webinar will be available on our website, and a link will be sent directly to you. Our thanks to Ken for his time and expertise, and to you for attending. Please don't forget to check the website for any additional webinars or roundtables you would like to attend this week. Thanks so much.
And thanks, everybody.